Okay, so let's talk about trig and inverse trig functions. So I'm not going to review everything. You're supposed to know. You're basically supposed to know it already. I'll review some important stuff that we're going to use though, and then periodically, whenever trig functions come up, I'll probably remind you of whatever else we need other than this. So yeah, here's your basic trig function sine x. I drew the graph here. The domain is all real numbers. The range is from -1 to 1, including -1 and 1. This is not a one-to-one function because it fails the horizontal line test. And yeah, this is the basic shape of it. So sine of 0 is 0, and then it reaches its peak at pi over 2. And then it comes back down and it hits 0 again at pi, and then it hits its low point at 3 pi over 2, which is halfway in between pi and 2 pi, and then it's back up to 0 at 2 pi, and of course it just repeats. It has a period of 2 pi, so it goes forever this way and this way. Cosine is similar. Cosine is, I mean, the graph is actually just a shift of the sine graph. If I took this picture and moved everything pi over 2 units to the left, I would get this picture. So the domain is still all real numbers. The range is still the same. It's still not one-to-one. It fails the horizontal line test. And yeah, so cosine of 0 is 1, and that's like the highest point. And then it has a period of 2 pi again, so it goes forever in both directions. Let's talk about tan x. Right, so here's a graph of tangent x, and I already realize that I made a mistake. The domain of this is not all real numbers. Tan x has these vertical asymptotes at x equals pi over 2, 3 pi over 2, and so on. So I can describe the domain as follows. X just can't be any of these numbers where there's a vertical asymptote. So pi over 2 is one of them, and then how will I describe the rest of them? Tangent has a period of pi, so this picture repeats itself every pi units. So if this is a value that x can't be, then what I can do is just all right, pi times n, this just represents, when I write the letter n, that represents any integer. So this is pi times any integer. So writing this represents all of these numbers. It represents pi over 2, it represents 3 pi over 2, and all of them. So the domain is all real numbers except for these ones. The range, I didn't make a mistake, the range really is all real numbers. The y values go all the way from -infinity to infinity. And this is not one-to-one, because if I draw a horizontal line, it crosses many times. Okay, so trigonometric functions have their name. I mean, the sort of trigon part of the word trigonometric is referring to triangles. So these are relevant to triangles. And so here's a right triangle, and say this angle is theta, and we typically call this side, if we're interested in this angle, we call this one the opposite because it's like across from that angle. We call this one adjacent. Adjacent is just a word meaning next to. So this edge is next to the angle. Of course, the hypotenuse is also next to the angle, but we call the hypotenuse the hypotenuse. The hypotenuse is special. It's the longest side. So this is how we call these: opposite, adjacent, and hypotenuse. And sine theta is opposite over hypotenuse. Cosine is adjacent over hypotenuse. tan theta is opposite over adjacent. Tan theta is also the same as sine over cosine. And if you just do sine over cosine and realize that this one's opposite over hypotenuse and this one's adjacent over hypotenuse, you'll realize why these are the same. There's a couple of nice triangles you should remember that will help you find sine and cosine of various angles. This is the 45, 45, 90, and this is the 30, 60, 90. So, for example, of course, I wrote these in degrees, and you should know how to convert. Basically, pi, if it's in radians, becomes 180 if it's in degrees. So if it's this many radians, then it's 180 over 4, which is 45 degrees. So if I want sine of pi over 4, that's sine of 45 degrees. And sine is opposite over hypotenuse, and that's this over this, 1 over root 2. Now, I'm not too picky about rationalizing denominators. It's not an important thing to me. However, since many people are, let me remind you that's the same as root 2 over 2. Okay. Sine and cosine and tangent are also, we can also talk about them in the context of the unit circle. So here's the unit circle. It has a radius of 1 and it's centered at the origin. And if I draw an angle of theta, like I start measuring my angle from here, this is the positive x-axis. It's the x-axis, but it's the part going to the right from the origin. So I start measuring from there, and then I measure out an angle of theta, and then I draw that line segment. And I look at the point where that crosses the circle. The coordinates of that point are, the x-coordinate is cosine theta and the y-coordinate is sine theta. This can also help you find the sine or the cosine of various angles. It can also help you find the tangent because actually tangent is the slope of this line segment. Because, well, yeah, if you think about the slope of this line segment, the slope is rise over run, and the rise would be this y-coordinate, and the run would be this x-coordinate, so the slope is this divided by this, and we know sine over cosine is tangent. Also, since we're talking about the unit circle, here's a picture with several points labeled. I labeled the very top, which is, of course, 0, 1, and that's easy to figure out. This is a circle of radius 1, and it's centered at the origin. And I also labeled the very rightmost point, which is 1, 0, and that's similarly easy enough to figure out. And then I labeled these points, which basically follow from remembering these triangles. Right, for example, if theta is pi over 6 is 30 degrees, and based on this triangle, the cosine of 30 degrees is adjacent over hypotenuse, so this over this is this x-coordinate. And sine, the y-coordinate, sine is opposite over hypotenuse, so this over this is this y-coordinate. And then similarly, to get this point, you would look at the 45, 45, 90 triangle. And to get this point, you would look at this triangle again, except you'd look at it from the perspective of the 60-degree angle, because pi over 3 is 60 degrees. And by the way, of course, if I'm looking at this 60-degree angle, this one's the opposite and this one's the adjacent. So which one you call the opposite and which one you call the adjacent depends on the angle that you're looking at. Okay. What's next? Inverse trig functions. So I put quotes around inverse. these are not, strictly speaking, inverse functions of the original trig functions. In order to have an inverse, a function needs to be one-to-one. Because if a function isn't one-to-one, one way of explaining this is to take a function that isn't one-to-one, that means it fails the horizontal line test, and then you flip it, because we talked about how the graph of an inverse is just the reflection of the original graph on the line y equals x. So you would flip it, and then the new graph, because the original graph fails the horizontal line test, the new graph will fail the vertical line test. So if a function isn't one-to-one, it can't have an inverse. And the functions we're talking about, trig functions, aren't one-to-one, so they don't have inverses. However, that doesn't mean we have to just give up on even talking about what we're trying to talk about. Here's what the quote-unquote inverse functions really are. You can call them partial inverse functions, because it's like if I just sort of cover up, say, part of the graph, like from here to here, of sine x. So I'm trying to cover up everything, but there's just a part that starts at the lowest point. So there's the lowest point at minus pi over 2, at an x-coordinate of minus pi over 2, and then a highest point at x equals pi over 2. And if I just look at this part of the graph passes the horizontal line test, because I cut off I cut off the other places where a horizontal line would cross the graph. And sorry, the paper's moving around, but yeah, so I want to take just the part of the graph from about here to about here. And I'll take that graph and flip it, like do the mirror image along the line y equals x. And I get this picture. If I were to have flipped the entire graph, of course, this would go like, it would sort of zigzag upwards forever. And that wouldn't be a function, because that wouldn't pass the vertical line test. So that's why we only take part of it. And we call this, it looks like sine to the -1 power. This really is not indicating a power, though. This is indicating, it's supposed to say inverse. Another way people write this function, which frankly this is better, but unfortunately it's a lot of writing, they write arcsine. Anyway, the domain is -1 to 1, and that's precisely because the range of the original sine function was -1 to 1, and when you flip it, basically the y coordinates switch with the x coordinates, so the range sort of becomes the domain. The range is minus pi over 2 to pi over 2 of this function, and it is 1 to 1. It passes the horizontal line test. Similarly, here is arc cosine x. It has the same domain. Its range is from 0 to pi. And by the way, this is the result of, let me do this again. Cosine doesn't have an inverse, so we do this. I'm going to cut it off here and here at 0 and pi. So we just look at that part of the graph, and we flip that part of the graph. And that's how we get this. And that may explain why the domain and range is what it is, just based on where we cut the graph off. And it is 1 to 1. For tangent, okay, sorry, but bear with me one more time. The original tangent looks like this. It doesn't have an inverse because it fails the horizontal line test. I cut it off here and here, right at the vertical asymptotes. And if I cut it off there, then it passes the horizontal line test. So I'll just look at this part, I'll flip that graph sideways, and call that arctangent. And that's what we have here. The domain is all real numbers. Since the original graph had vertical asymptotes at minus pi over 2 and pi over 2, this graph has horizontal asymptotes at minus pi over 2 and pi over 2. And the range is from minus pi over 2 to pi over 2, not including either one, because it basically this line becomes very, very close to negative pi over 2, but it never really crosses it. It is 1 to 1. And yeah, so let me sort of expand on my comment before about how this isn't a power. When I write arcsine like this, it looks like sine with a -1 in it, and the -1 is written above, in in a superscript place where we would normally write a power. This doesn't mean a power. If I wanted to do sine of x to the -1 power, I would write it this way, and that's not what this means. Unfortunately, this is a confusing notation because we do often write a positive power. If I want to talk about a positive power of sine, I often do write the power here in the same place where we would write the -1 if we were talking about inverse sine. And when we write something like this, we really do mean sine of x to that power. It's the same as just writing this in parentheses to that power. So yeah, I mean, if I could go back in time and convince mathematicians that we should have a different notation, then I would, but this is pretty well ingrained at this point. So please just remember that this is not the same thing. When you write a -1 in what looks like a power on top of a trig function, that means the inverse trig function. It doesn't mean a power. Okay. So there will be times in this class when we have to find all solutions to an equation involving trig functions. So let's talk about how to solve these equations, and in particular, how to find all solutions. Sometimes you only want solutions between 0 and 2 pi, or sometimes you only care about solutions between something and something else. And we can talk about that too, but the most important thing is to be able to find all solutions ever. If you can find all solutions, then you can definitely find all the ones between 0 and 2 pi, or whatever range you're really looking for. So here's how this goes, and I've tried to make this so that it kind of makes sense, so that it's easier to remember. First of all, what if I'm trying to solve something like this? Sine theta equals some particular number a, and I want to find all the numbers theta that satisfies this equation. I drew this picture. This picture helps me remember what to do. Remember, sine theta is the y-coordinate of a point on the unit circle. So I'm looking for points where I'm looking for angles where the y-coordinate is a. So I drew a line, and this is representing points where the y-coordinate is a. It's just a horizontal line at a height of a. And so I would be looking for the points on the unit circle that are like that. In other words, I'm looking for basically this angle and this angle. This angle, this first one, is just the arcsine of A. Arcsine, like, basically, that's just the result of taking arcsine of both sides. And that's like that's going to give us an answer between minus pi over 2 and pi over 2. So that'll give us an answer between here and here. And sure enough, it did, that this angle is between here and here. But there's always going to be infinitely many solutions to these things, basically. So this angle, basically you can just take this angle and you can go around 360 degrees. You can go around another 360 degrees. So I'll take this plus any multiple of 2 pi. But there's even more, because there's this angle. So what's this angle? This angle is what I just underlined. It's pi minus arcsine of A. That's basically because the circle is symmetric, so this point over here is a reflection of this point over here. So if I want to figure out this angle, basically this angle is the same as this one, which is arcsine of A. So if I want this angle, it's just pi minus arcsine of A. And then you can take that, and again, if that's an answer, then you can go around and around. You can do 360 degrees as many times as you want. So I'm going to add a multiple of 2 pi n. And that's all solutions. Let's talk about the same idea, but for cosine theta equals A. So remember, cosine is the x-coordinate of a point on the unit circle, so I draw a vertical line. These are all the points with an x-coordinate of A, and then I would be looking for this angle and also this angle. This angle is arc cosine of A, and of course I can add any multiple of 2 pi to that. This angle down here, because again of the symmetry of the circle, this angle down here is just the negative of this angle up here, so it's just negative arc cosine of A plus any multiple of 2 pi. Let's talk about tangent. How do I solve tan theta equals A? For this, I draw the same picture. I draw the unit circle, and I remember that, so just remember that, oops, where did we go? Where is the stuff with the, oh, whoops, no, it was right here. Sorry. Cosine is the x-coordinate, sine is the y-coordinate, and that's why we did what we did. When we were doing sine, I did this. When we were doing cosine, I did this. And tangent, which we're about to do, tangent is the slope of the line segment. So if I want the tangent of theta to be A, I'm going to draw a line whose slope is A, and then find the angle that will give me that point. There's going to be one in the, so the range of arctangent is from minus pi over 2 to pi over 2. So there's going to be one answer in between here and here, like basically the right side of the circle, and there's one that's going to be on the left side of the circle. The one on the right side of the circle is just called arctangent A. And actually, again, due to the symmetry, this one, the one on the other side, is just 180 degrees off. So, and basically you can go around and around. You can go 180 and get this answer. You can go another 180 and get back to this answer. So you can, for this one, we're adding any multiple of pi, which is a bit different because we've seen a lot of 2 pi n's, and this one just has a pi n. And that's it. That's how to find all solutions of equations that are like this. Let's Yeah, so actually maybe this will be a little bit of a long video, but I'm almost done. So let's do a couple of examples. We're going to find all solutions to this, and this will be kind of easy because of what we just did. So I put some stuff around the cosine x, but we know what to do. We just want to get that by itself. So I'm going to subtract the 3, and then I'll get a 1. I'll multiply by a half. And now I'm down to cosine x equals a half. So what am I going to do? I'm going to run through this. So, and I know, like I was saying, this gives you all solutions. And actually, let me make this clear. All of these things that I told you on the other page, this is giving you any and all solutions to the equation. So what I'm about to do is an if and only if step. I don't need to worry that I'm finding extraneous solutions, nothing like that. So what did I have? My answers were, so my first answer was arc cosine A plus 2 pi n. And I can simplify this. What is the arc cosine of 1/2? Well, the cosine is the x-coordinate of a point on my unit circle. And so if I want to find where that would be 1/2, right, like to find the arc cosine of 1/2, I'm looking for an angle whose cosine is 1/2, so its x-coordinate should be 1/2, and here I see a point whose x-coordinate is 1/2, and the angle that I would use to get that is pi over 3. Let's not forget the other one, because, whoops, and I am jumping all over the place now. Back to here. The first one is this. The second one is just negative arc cosine of A plus any multiple of 2 pi. So basically, since this was pi over 3, the other one's going to be negative pi over 3 plus 2 pi n. So let me just put a box around this. This describes all solutions. Okay, then we have just a couple of other kind of randomish examples, but I wanted to do one like this because there's one on the online homework that's coming up. How do you do a trig function of an inverse trig function? Here's how I do it. I'm going to let theta be the inside. And when I say theta is arctan of x, that means that, tan of theta is x. So what I'm going to do is I'm going to draw a triangle representing theta is going to be here. And what is tangent? If you remember, in the context of right triangles, tangent is opposite over adjacent. So I want the opposite over the adjacent to be x, and one cheap way to do that is to just make a fraction artificially by putting x divided by 1, and then I'll just label the opposite as x and the adjacent as 1. Now, triangle's getting a little encroached on, so let me cordon off some space there because I wanted to put down something for the hypotenuse. You can use the Pythagorean theorem. This squared plus this squared equals this squared. So I trust that we are all good enough to say that means this is the square root of 1 plus x squared. If you don't follow that, you can write down this squared plus this squared equals this squared and then solve for this. So where are we? What did we want? I wanted the cosine of this, and this thing in the inside is what I called theta, so what I really want is the cosine of theta, and off of this picture I can get it. Cosine is adjacent over hypotenuse. Then let's find the domain and the range of this function for our next example. So for this, we are basically just going to recall the domain and range of arc cosine, because this is a function involving arc cosine. So what do we know? The domain, in other words, the set of values that you're allowed to plug in here is between -1 and 1. So I just have to make sure that the number that I'm plugging in is between -1 and 1. So here I have, it's one of these three-sided inequalities, so I'm allowed to do anything as long as I do the same thing everywhere. Or, you know, I guess if I were to divide by a negative number or multiply by a negative number, then I would do it to all three things, and I would switch the directions of the inequalities. But I don't think I'm going to do that in this example. Anyway, I'm going to subtract 6 from everything, so -7, 3x, and -5, and I'll divide by 3, -7/3 x, -5/3, and that's the domain. Like this. So yeah, I'll put a little box around that to make it clear that's the domain. We also needed the range. The range is going to be easy because the range of arc cosine was from 0 to pi. And so we're plugging in something funny to arc cosine, but then we're not doing anything after that. Like I'm not multiplying by a number or adding a number or really anything. So the set of values that this can take is really just the set of values that arc cosine can give us. And that's, it's, in other words, it's just going to be the same range as just arc cosine of x, which is 0 to pi. Okay, so then that'll be it for today's lecture.